Welcome back to Calculus 2, Section 7.1, Parametric Equations. Let's start off with the definition of parametric equations. And to motivate the definition, let's take a look at our home, the Earth. Looking down on the Middle East, Africa, little blue dot to represent the Earth. The Earth orbits the Sun. The Earth orbits the Sun in an ellipse. And we can watch that Earth go about the Sun. The Sun will occupy one of two of these dots, F1, F2. Those are known as foci. F1 is a focus, F2 is a focus. Bring in the Sun as one of the foci, F2. And then we have a picture where the ellipse given by these two foci describes the orbit of the Earth. If you think about the Earth, we can suppose that the current location corresponds with the beginning of the year, January 1st. That at some later date, April 2nd, we'd be in this location here. At a later date, at day 182, we'd be at this location here. When the day is 274 of the year, we'd be at this location. And then when we come into December and then start getting into January the next year, we're back in our location. So what's going on is we're letting t be what's called the parameter. That here at this point, the parameter t is being set equal to some initial value, t naught. In our example, t naught was the value 1. That as time goes by, as the days tick away, that the location of the Earth moves from some initial location. Let's say here we're placing an xy axis, so that we can observe the location as x being 0, y equaling b. And then at some later date in the year, maybe the Earth sits at this location. But since we allowed ourselves an xy axis, we can identify that point in the plane as some x coordinate and some y coordinate. But that those points, x and y, will depend on the day of the year. Let's say the day of the year is this value, t1. And note what's going on is that we have an orientation to this ellipse. The ellipse, when we give it this parameterization of x of t, y of t, we call the ellipse a parametric curve. And in our choice of parameterization, we inherently pick an orientation. So the parameterization comes along with an orientation. And to sketch that out, we need to indicate that orientation. Nice. So formally, here's the definition. F and g are going to be continuous functions of a variable t on some interval. So the interval will have a beginning point and an ending point. Then we let x be the output of the f and y be the output of g. These two equations taken together then are called parametric equations. The variable t is called the parameter. And we can denote that with this notation here, where the curve C is the ellipse, described by these two equations called the parametric equations. The curve C is then parameterized, and the curve C is called a parametric curve. With parametric equations, these two equations, no, plural, and that is the definition of parametric equations. How about graphing? Let's take a look at graphing, and we're going to use Desmos to assist us. All right, we're looking at a circle. The center of the circle is the origin. The red curve is a circle of radius 1. The red curve, we have an orientation which is clockwise. The red curve is then the parametric curve we're calling C. This parametric curve is given by the parametric equations, one for x and one for y. We're letting x be given as sine of the parameter t, y be given by cosine of the parameter t. So that if we pick any point on the red curve, then that point is determined simply by picking a value for t. Let's see how to enter this into Desmos. In Desmos, we can use 3 different cells to produce this sketch. In the very first cell, I'm typing in an ordered pair, parenthesis, sine of t. Desmos is smart. It knows that t is a parametric parameter. And because of that, Desmos will prompt me for the interval. I'm letting the interval of the parameter t go from 0 up to 2 pi. That's 1 full period of these trig functions. And then for the x-coordinate, I use sine. For the y-coordinate, I use cosine. Very easy. Now, if I want to make this blue dot on the red parameterized curve, I simply specify a value for the parameter t. And to allow that value to vary, I've introduced a new slider, capital T. So when I type in capital T, Desmos recognizes I want to make a slider. It prompts me, it asks me, I say yes, and then I get the third cell. So let's see what happens if we press play in Desmos. Then the blue dot would move in the orientation of the curve, which is clockwise in this case, so that the blue dot has gone from, let's say, a value 3 towards a value 10. Nice. Here's an assignment for you. Very similar. You have a parametric curve given by x equals cosine of t, y equals sine of t. This is slightly different from the previous example we just saw. Specify how the two differ. And you're told here how they're going to differ. Here's another one. Nice. Let's take a look at this example here, where instead of the parametric curves given by trig functions, we're using polynomials. So this is sketched out. We can watch a point on the curve traverse from one end to the other end. That is then going to indicate that the curve has this orientation specified by the arrows. And we can observe that by taking a look at the interval for the parameter. And when we plug in t equals -2, we'll get this point here. -2 plugged in for t, that'd be 4 minus 3 would be x equaling 1. And then y would be -8. -4 plus 1 would be y equal -3. Nice. Same thing if you plug in the upper value of t equaling 3, you'd get this ending point. Fantastic. You give it a try. Plot this parametric curve given by algebraic functions and indicate the orientation. Then note, because we have a radical involved, that will naturally prescribe a restriction on the parameter t. In first year calculus, we don't use complex numbers, so t must be taken so that the radicand is non-negative. Nice. Now, if we look at the book would have us plot points, and that's very nice, but using the graphing calculator, such as Desmos, is very convenient. Another important way to produce sketches of parametric curves is by eliminating the parameter. Let's look at some examples. Here's a very elementary example. If we take parametric curve C given by parametric equations x is the parameter, y is cosine of the parameter, then this is essentially just y equals cosine of x. And indeed, that's what the parametric curve would look like. That was pretty simple. Let's look at some more involved examples. Here, this is similar to what we had before, x equals sine of t, y equals cosine of t, but we have some values out in front of it, some coefficients. And what we can do is take advantage of the Pythagorean identity. Cosine squared of t plus sine squared of t is constant 1, unit 1. Now, if you take each of cosine squared of t and sine squared of t and multiply them by 1, and then make your choice of 1 so that you can relate it back to the parametric equations. So for the cosine term, if we want to square cosine, then squaring y would produce 4 cosine squared, so 4 over 4. And then for the sine squared, if you look at sine squared, you'd produce, and also square the 3, you'd get a 9. So 9 sine squared would be the same thing as x, but 9 over 9 is just 1. So making the substitutions in the numerator, we get y squared over 4 plus x squared over 9 is equal to 1. And this, you can recognize, is an ellipse. So we can sketch out an ellipse. But note that this is a parametric curve, so it isn't sufficient just to sketch the curve, but you must also indicate the orientation. And the orientation is clockwise, since x is being set equal to sine and y is set equal to cosine. So we indicate the orientation. Nice. Here are some for you to play around with. This will also be an ellipse. In this one, you want to use the double angle identity for sine. In this one, you want to use that the natural log is inverse to the exponential e. In this one, you can simply solve for t and substitute. And along those same notions, you can solve for t, substitute. And then since the natural log is not defined everywhere, that's going to place a restriction on the domain. Nice. So we had graphing using Desmos, and we have graphing by changing from a parametric form into a rectangular form. Let's finish this video by looking at some special parametric curves. A cycloid. Cycloid is very interesting. Let's say that we have a wheel. The center of the wheel is given by the red dot, and then paint a point on the wheel, and then let the wheel roll. Then that point that we painted in orange would trace out this blue curve. All right, now up above we have two parametric equations, one in red and one in black. The one in red is describing the location of the center of the wheel, the red dot. Note that that red dot is always at a height of 1, and then it's just moving rightward, so x equals t, y equals 1. Now, the wheel itself has a clockwise motion, and to describe that, we can use x equals negative sine t, y equals negative cosine t. So putting these two parametric equations together, summing them, would then allow us to describe the location of that orange dot. And that's called a cycloid. By watching the motion of the orange dot traces out the blue curve called a cycloid, which is the sum of the center of the wheel and the clockwise motion of a point on the wheel. All right. That's an example. And then building off of that example is something called a hypocycloid. This one gets rather involved. Let's take a look. Previously, the wheel traveled on the earth, on the floor. Here, the wheel is going to travel about this outer circle in red. The outer circle will have a radius given by A. The inner circle will have a radius given by the difference of an A and B. In this particular example, we're taking A to be 6 and B to be 2, so that 6 minus 2 is 4. Now, let this purple circle be the rotating wheel, and let that rotating wheel have the radius of B. Thus, the rotating wheel is going to rotate about the red circle, and the center of the rotating wheel will be on the blue circle. Like before, pick a point on that rotating wheel and call that P. And then it turns out that the number of times the point P will touch the outer red circle is related to the ratio A over B. Here in this example, A over B, we're taking to be 3. Looking at what curve is traced out by that point P produces a hypocycloid. And this one is a little bit more involved, but it's the same type of notion that we look at the center of the wheel in blue parametric curves, and then the rotation of the rotating wheel given in purple, and then adding those two together produces parametric equations for the black hypocycloid. And then you can copy this one down as the form. You simply have to plug in A's and B's, plug that into Desmos, and then it will sketch it out for you. Let's look at some particular examples. This is a particular example where the ratio of A and B is 3. Here's a hypocycloid where the ratio of A and B is 4. And then 5. And then now let's jump to pi. Pi is an irrational number. And as such, we're not going to get a finite number of times which the point P is going to touch the outer circle. What will happen, because that pi is an irrational number, is that it will touch every single point of the outer circle. And thus, it's going to fill the entire space. Which is a very nice idea. Excellent. So try that with this ratio, A over B equals rad 2. You can pick your favorite A value and then solve for B. And then when you do that again, because rad 2 is an irrational number, you should produce a space-filling curve. See if you can put words down to explain what is happening. Excellent. And then here are a few other parametric curves that you can plug into Desmos. Note the interval on the parameter t. And note that this is providing both x and y given by sine, but the parameter for sine is either 4t or 3t. Let's see what curve is produced. Spiral curve, where we take cosine of t, but we add the variable, the parameter, as a coefficient, and then use this interval on the parameter. And that is section 7.1 on parametric equations. Thanks for watching. See you on the next one.